All right, let's get into chapter 5. We're going to continue with linear programming, and we're going to look at a technique known as data envelopment analysis. Sounds pretty impressive, doesn't it? Well, let's go ahead and get started. All right, so what is data envelopment analysis, or DEA as we will call it from here on out? Well, for one thing, it is a special form of the allocation model. Okay, so we've already seen the allocation model in our in previous chapters concerning concerning linear programming, where we allocate resources to specific tasks or processes. It has a distinct application and interpretation. It's actually kind of a narrow a method that has a narrow range of uses. Okay, but it can be useful. All right. Unlike most linear programming applications, DEA is an ex post tool. In other words, it is used to evaluate past performance rather than predict future performance. And it is a relatively new technique. It's really only been developed and used since the 1970s, although its use is picking up in research lately. Okay, so let's take a look at the main components. All right, the main elements of a DEA model are decision making units. Okay, these can be bank branches, hospital clinics, regional offices, government offices, departments within an organization. Okay, the DMUs should be as homogeneous as possible with well-defined inputs and outputs, and they should be separately managed. All right, we want to compare them to each other. All right, so we're going to gauge the relative efficiency of one DMU against other DMUs. All right, which is why they really need to be homogeneous with the same well-defined inputs and outputs. They need to be separately managed, or else we don't really get an effective comparison. Okay, but all of the inputs should mean the same. The outputs should mean the same. This usually means that these are branches or offshoots of a single organization, although it doesn't necessarily have to mean that. So let's take a look at a kind of initial example of DEA, very simplistic. All right, let's take a look at farms. We have 5 farms, and each have a certain number of cows, and those cows give milk. All right, the cows are the inputs, and the milk is the output. All right, and the productivity measure on this screen is simply milk divided by cows. Okay, and then we have an efficiency measure over on the right hand side. Okay, and so we have judged farm number 4 to be the most efficient. Okay, because it has the highest productivity value. All right, now this does not mean that farm 4 operates at perfect efficiency. Okay, it just means out of these 5, using the inputs and the outputs that we have defined, it has the highest productivity. So we're going to arbitrarily call it efficient. All right, and then the rest of the efficiency values are simply measured in relation to the most efficient farm. Okay, and so the question is, what good is this? Okay, how does this help us? Well, as you can see, that if these 5 farms, for example, were run by the same kind of farming cooperative, we would have a relative way of judging the efficiency of one against the other. All right. Again, it may not be real clear at this point how effective this is, but this is fairly straightforward. All right, so let's talk about DEA a little bit more. Most decision-making units will have multiple inputs and or outputs. All right, in our previous example, we only had one of each just for demonstration purposes. But most organizations, as you know, have different inputs and different performance outputs. Now, because they will have multiple inputs or outputs, they're going to need to be weighted to quantify into a performance measure. All right, so the ratio of outputs to inputs is what our performance measure is going to be. Now, the question is what are we going to, how do we decide what the weights are? All right. And in fact, we don't get to decide what the weights are. The weights are not determined beforehand, but by the analysis that we're going to perform. Now, that may seem a little bit weird to you. All right. Rightly so. Okay. But kind of follow along and you'll see the reason for it. So then we can normalize the productivity values by comparing them to the DMU with the highest productivity and scaling the results by setting the highest productivity rating to 1. And that is what we did in the farm example. Okay, we took the farm that had the highest productivity, set it equal to 1, and then scaled everything else by its relation to the most efficient, or what we judged to be the most efficient. So let's take a look at a little bit more complex example. All right. So here we have bank branches. All right. And so we have 5 of them, 5 branches. These are our decision-making units. That has one input, and that's the expenses of the organization or of the branch. And the outputs are the amount of loans and deposits. Okay. Now, you may be asking, how can all 3 of them be efficient? All right. And the explanation is this: there exists a pair of weights for each of these branches that has the highest productivity, that gives it the highest productivity. Okay. Obviously, all the expenses are the same, so it doesn't matter what it's weighted. But for loans and deposits, there is a set of weights for branch 1 that when they are used, give it the highest productivity. There is a set of weights for branch 3 that give it the highest productivity, and there's a set of weights for branch 5 that give it the highest productivity. Now, obviously, these are different weights than, so the weights for branch 1 are different than the weights for branch 3 and branch 5. Okay? Probably getting a little bit confusing, but hang in there and you'll see. And so the question is, what about 2 and 4? All right, what does that mean? Well, we'll show you that in a moment. Let's take a look at the previous example graphically. Okay, we have deposits and loans on our y-axis and our x-axis. All right, and we have graphically plotted the 5 branches on this graph. Okay, now, so now if we draw a line between our efficient branches, 1 to 3 and 3 to 5, we can call this kind of an efficient perimeter, if you will. And now let's take and extend the line from the origin through 2 and through 4 until it reaches our efficient perimeter. Okay? And where it intersects that line, we call that 2 prime and 4 prime. These are known as hypothetical comparison units. You were wondering, or I hope you were wondering, where we got the efficiency values for 2 and 4. And this is how we do it. Okay? The HCUs, 2 prime and 4 prime, share the characteristics of the efficient branches, all right? Greater output, essentially. But they retain the same ratios as the inefficient branches, all right? And so the length of 2 is 83% of the length of 2 prime, and 4 is 92% of the length of 4 prime. And if you go back and look at the previous slide or a couple slides ago, you will see that the efficiency measure for 2, branch 2 is 0.83, and for branch 4, it is 0.92. Now there's one other topic to introduce, and that is the concept of the reference set. All right. So branches 1 and 3 form the reference set for branch 2. In other words, we figure out we figure out the value, the efficiency value for 2 by comparing it to branches 1 and 3. We figure out the efficiency for branch 4 by comparing it to branches 3 and 5. Now, as we get more inputs and outputs, graphically, it's almost impossible to graph. Okay, so this is not a method that I'm showing you right now. This is not a method really that we use in any practical way. It's just here to show you, to give you a better idea of what we're talking about when we do DEA analysis. So now let's take a look at this in our spreadsheet model. We're not going to analyze things graphically. We're going to use Excel. Okay, so this is what that simple DEA model looks like in a spreadsheet. All right, the rows represent the DMUs, the decision-making units. Okay, the columns represent the inputs and the outputs. All right. We will analyze one DMU at a time, and you can see where the red arrow is that we have defined that in the spreadsheet. All right, and so the decision variables are the weights. Okay, these are the weights that we're going to assign, or actually, as you can see, they are yellow. So these are our decision variables, and so Solver will actually determine the weights for these variables. Okay, and so it's going to find the set of weights that will give this the absolute best efficiency that it can. All right. The objective is the sum product of the weights and the outputs. All right. And then the input is scaled to 1. All right. We almost always do this. We set the constraints so that we come up with a value that scales the input value to 1. This doesn't have to be done, but it just makes things, we tend to think in terms of efficiency, in terms of percentages, okay? And this just makes it easier if we scale everything to 1. And so efficiency is constrained to be no greater than 1. Output minus input is less than or equal to 0, because we're saying that efficiency is essentially output divided by input, right? Well, when we put those terms on the left-hand side of the equation, that's what it comes out to be. Output minus input is less than or equal to 0. So all of your DEA analysis is going to look very much like this. It might have more input columns, it might have more output columns, but it's going to look pretty much like this. So we analyze branch 2. Okay, the previous slide was branch 1. Now we analyze branch 2, and if you will recall, we ended up with about an 83% efficiency. Okay, the input value is still 100, but in this particular case, but it can be different. It's not really reasonable that in real life input values are going to be equal to each other. Okay, it can be different, and it doesn't affect our analysis at all. Okay, now take a look. Branches 1 and 3 have binding constraints. Okay, and if you recall, branches 1 and 3 had an efficiency of 100%. So when we do DEA analysis, we look after we've run Solver, we look for binding constraints. And what that tells us, a binding constraint is essentially the reference set for this branch. Okay, when we see that the efficiency is less than 1, we look for, in other words, the green cell, our objective cell, is less than 1. We look for the binding constraints, and that tells us that it is the reference set. Okay, now, so we're analyzing one branch at a time. Okay, so basically we go over here and we put a value in. We put 1 in and we run solver, and then we put 2 in and we run solver, and 3 in, and so on. All right. Well, that's pretty tedious. Suppose you've got 20 DMUs. All right. That can be a real hassle. All right. So what we do is we use the index function in Excel and solver sensitivity, which we introduced in the last chapter, to automate the process. Now, the index function itself takes the form of index and then the array, the row, and the column. Okay. So, for example, in cell D10, all right, it says index C2 to E6. All right. So it references this array. Okay. And then I9. All right. So it looks over here and gets this value, whatever is in the branch box. And then lastly, the column is column 2. Okay. And so it looks in this array in the first row and returns the value in the second column. And if you go down here, you see that is exactly what it has done. All right. These are the outputs of that particular row. Okay. So D11, the same thing, and C13, the same thing. We use the index function. You'll get the hang of this. It's not that difficult. And then we use solver sensitivity to value the cell in I9 from 1 to 5, and it will create a table showing the objective, which is our efficiency, and the input and output weights. All right. It's quite a handy solution. And so this is what it looks like, slightly reformatted. Okay, we've gone through branches 1 through 5. The expense, as we know, is the weight is the same, and then our loans and deposits are our weights. Okay, and so for example, for branch 1, we ignore the loan output completely, and we only care about deposits. All right. For branch 3, it's O2 and O2 for both. And then for branch 5, we ignore deposits and we focus on loans. Okay. And then, so on the right hand side is where we get our efficiency values. Now, let's talk quickly about something called indexing. This is not to be confused with the index function in Excel. All right, this is something that we do manually. All right, it's not necessary to present input and output values in their absolute values, but rather relative to each other in percentages. Okay. What this does is it allows the calculation of the weights to be closer in magnitude, order of magnitude, allowing for a more intuitive interpretation. And so in order to index, what we do is we set the highest value for any input or output to 100 and the other values as percentages relative to that highest value. Okay, so here's an example. In the bank example, this is the original. All right. And so obviously all of the expenses, there's no need to index them because they're already at 100. They are all at the same value. But in terms of loans and deposits, you can see that for loans, number 5, branch 5 has the highest value. And for deposits, branch 1 has the highest value. So when we do it in index form, all right, branch 5 has a 100 in the loans area, and branch 1 has a 100 in the deposits area, and everything else is simply a percentage of those highest values. Okay? This does not change our analysis at all. Okay? It just puts things kind of in the same order of magnitude and actually solver sometimes runs a bit more efficiently when that happens. Okay, or when you are presenting your results, it might be easier for people to understand when they are when the results are roughly the same order of magnitude. So as you can see, here is our spreadsheet model using indexed values rather than the original absolute values. And the weights are going to be a little bit different because they're operating on different values from above, but essentially the results are going to be the same. Branches 1, 3, and 5 are going to be efficient. Branches 2 and 4 will not be efficient. They will have the same efficiency values. Okay? And so here you can see it. These are the results using indexed data. And as you can see, the results, especially the weights for loans and deposits, are a little bit closer together in terms of magnitude than they were using the raw data. But as you can see on the right-hand side, these efficiency values are still the same. If you do a problem indexed and you get a different result than non-indexed, then you have done something wrong. Now, let's figure out what to do with hypothetical comparison units and reference sets. Okay, so far we have shown you how to identify efficient and inefficient DMUs. Okay, and so the question then is, what do we do about the inefficient DMUs? What good does it do us to know that they are inefficient? All right. Well, one, by identifying the reference set, okay, the efficient DMUs that we use to identify the inefficient ones, then we can construct the hypothetical comparison unit value. All right. And then once we've done that, the HCU should give us an idea of what improvements are possible for the inefficient DMU. Really, the whole point of this is to identify. It's actually more about identifying inefficiency than it is identifying efficiency. Okay? And so think about that, and we'll explore that more as we go along. All right? But if we have 5 branches that are efficient and 2 that are inefficient, all right, really our focus is on the 2 that are inefficient. All right? Because we need to know how they can improve. Okay? And so constructing the hypothetical comparison unit can give us an idea of what improvements might be possible. So let's take 2 nursing homes. All right. Here we have actually it's more. It's 6 nursing homes. 2 of them are inefficient. All right, and 4 of them are efficient. All right. We have run our DEA and we've determined that there are a set of weights for reimbursed and private that give us efficiencies of 1 for DMUs 1 through 4. All right, but for DMUs 5 and 6, there are simply no weights. There are no possible combinations in the universe that will ever bring them up to an efficiency of 1. So here's our spreadsheet model for the 2 input, 2 output problem. And as you can see, that it is the analysis of facility 5. All right, we come up with an efficiency of 98%, which means it is inefficient. And so what we can do here, actually, the fact that we have a hard constraint on DMUs 1, 2, and 4 indicates our reference sets, but we actually need the shadow prices. So we can go to we can run the sensitivity report and get the shadow prices for our constraints. And anything with a positive shadow price indicates that it is a reference set. Okay, and once we have the shadow prices, we can calculate the HCU. All right, the HCU for facility 5 is the sum product of the shadow prices times each column of inputs and outputs. All right, so 342.125, for example, is the sum product of the values in staff hours times the shadow prices, times the entire array of shadow prices, and so on for supplies, and then reimbursed, and then private. And so we get this a hypothetical comparison unit for facility 5. Now, how does that help us? Okay, it might be an interesting intellectual exercise or mathematical exercise, but how does it help us? We'll see that on the next page. So, what does it mean? Okay, what does this HCU mean? Well, as you can see, the HCU 5 actually has the same outputs as Facility 5, but actually has slightly lower inputs. All right. So that means that the managers of Facility 5 can look to the management practices of our reference set 1, 2, and 4 for ways to lower their inputs. We can probably gauge that higher outputs are not possible in this case. All right, but there might be ways of lowering our staff hours, the amount that we spend on supplies, and so on. Now, Facility 3 was also efficient. Okay, but as you can see, the output mix is clearly different than facilities 1, 2, and 4. Okay, which is why it's not suitable for comparison. All right, so we're better off comparing to DMUs 1, 2, and 4. All right, because they have a mix that is similar. All right, and so we look to the efficient facilities in our comparison for our in our reference set to see what can be done in terms of gaining more efficiency. All right, and we use the HCU to judge whether we can increase our outputs, decrease our inputs, or perhaps both. Now, we operate on certain assumptions and limitations when we run DEA. Okay, and obviously, when we use the term efficient, we are only speaking of relative efficiency among the DMUs that are being analyzed. Data and development analysis assumes no prior judgment about the weights of the inputs and outputs. All right? And it may not be suitable for circumstances where the weights are known or even guessed at. Okay? And the fact that DEA uses completely arbitrary weights opens it to criticism. So, for example, as you saw, weights of 0 are permitted. We can just, if it suits us mathematically, we can just ignore an input or an output and say it has no bearing. All right. In practical terms, that may not be acceptable. And in fact, what some analysts will do they will impose a lower bound on the weights. They will not let them go to 0 because they say it's simply not reasonable to ignore an input or an output completely. So let's talk about lower bounds. All right. To prevent an input or an output from being completely ignored, we can impose a lower bound on any of the inputs or outputs. All right. And so the most common way of doing this is to put a minimum percentage on the product of the input or output and its weight. And this is known as the virtual input or output. And we'll show you an example of that. So here we have our bank example with a 10% lower bound on the outputs. Okay, what that means is we do not find it acceptable to be able to calculate efficiencies if it means ignoring one of our outputs, loans or deposits. All right, and so we create the virtual output. Okay, and that simply is we set it to greater than or equal to 10%, and we add that as a constraint. Okay, and so our outputs multiplied by our decision weight cannot be less than 0.1. All right, and so this is what it looks like in the final analysis. And so here's our results. As you can see, with the lower bound, what we end up with is two branches, branches 3 and 5, that are efficient. Okay? And notice that none of our weights for loans or deposits is zero. All right? We have simply not allowed them to be ignored. Without the lower bound, which was our original at the bottom there, we have three efficient branches, and the two of the efficient branches simply ignore. Branch 1 ignores loans, branch 5 ignores deposits. All right. So intuitively, you might say that the with the lower bounds actually makes a little bit more sense. If you end up with a lot of efficient DMUs, it kind of decreases the benefit of the analysis. Okay? And when you have an analysis that ignores an input or an output, you kind of think intuitively that perhaps this doesn't sound right. So we can impose things like lower bounds in order to add some weight to our inputs or outputs. Now, there's some additional considerations for DEA. Sometimes, and I mentioned this in the last slide, the number of efficient DMUs is so large that it doesn't really make for any meaningful analysis. All right. In this case, some analysts may want to do a tiebreaker among the efficient DMUs. And one way of doing this is by removing the normalizing constraint for the DMU. All right. In other words, allow efficiency greater than 1. All right. There is actually a more complicated but more equitable way of doing this, and that's by computing cross efficiencies. A cross efficiency is the average of the efficiencies computed by multiplying a single DMU's parameters by every other DMU's weights. Now, as a matter of fact, the whole tiebreaker scenario doesn't happen that often because we aren't as efficient, aren't as interested in the efficient DMUs and which one may be theoretically better. We're actually interested in the inefficient ones. And the reason we are is that because there's absolutely no scenario. Remember, we've calculated all the possible weights for these DMUs. And for the inefficient ones, there is no possible combination of weights that gives them an efficiency of 1. Okay, so what that means is by any particular measure of efficiency, they don't cut it. All right, that's why we focus more on the inefficient DMUs than the efficient ones, because the efficient ones, really, it's just the fact that we've come up with an arbitrary set of weights that gets them to 1. And that's not as useful as knowing that for an inefficient DMU, there is no possible combination of weights that ever gets them efficient. So they're the ones that we focus on. So, in terms of analysis, analysts must resist the temptation to include too many DMUs or too many input or output parameters. Okay, if you have too many decision-making units, the chances are the less likely they are to be homogeneous. All right, and they really need to be as homogeneous as possible in order to make this meaningful. Okay, too many inputs or output parameters endanger discrimination. In other words, you get too many efficient DMUs. The more inputs and outputs you have, the more likely you are to find some arbitrary combination of weights that will make them efficient. And so there is a rule of thumb, and that is 2 to 3 times the number of DMUs as the number of input and output measures together. Okay? Now, this is a very loose rule of thumb. All right? But if you think about it, too many DMUs means that they're most likely not going to be homogeneous. Too many input and outputs is going to mean that there are too many efficient DMUs. Neither one of those is what we want. So DEA is a fifth type of linear programming model. It is a tool, ex post tool, it just means after the fact, for evaluating past performance. But we have to be careful not to generalize our findings beyond the set of DMUs under consideration. All right. This is a very focused type of analysis. We can't take our insights here. We analyze, if we analyze 10 DMUs, we can make judgments about those 10 DMUs, but we can't generalize those findings outside of that set. All right, we have to be careful about that. But this can be a useful tool for doing an internal analysis of branches or departments or some kind of decision-making unit, decision-making units that are very much like each other. That's it, and we will see you again when we get to the next chapter.